Hello everyone, welcome to the Jones Seminar. Thanks for coming. It's my pleasure to introduce Rich Katz. Rich Katz is a great scientist, as you will see, some awesome work, very creative. He's always been very nice to me as a mentor, so I'm very pleased to have him here, talking to you all about some really cool work that he's doing. Rich did an undergraduate degree at a different Ivy League school called Cornell, somewhere over there in a different state. He then went to Italy and bummed around for a while. Good thing to do. And then he went to another Ivy League in that same state called Columbia. He worked at the Lamont Doherty Earth Observatory and did a PhD with Mark Spiegelman, working on volcanism and things like that. And he went to Cambridge in the UK. He worked with Gray Worcester on mushy zones and ice streams and things like that. Very exciting sort of icy things. And now he does a mix of all this volcanism, planetary science, icy moons, icy things at Oxford as a professor. So, and for my Engines 34 students here, I'm very Navi stoked about your lecture.
I'm really torqued, thank you. Right, thank you so much for the invitation to come and visit and give the Jones Seminar. It's an honor, and it's been a real pleasure, really, to be here. I've had a great time the last couple of days meeting people and hearing about what you guys are doing, seeing the amazing labs. It's an exciting place to be, and the weather here is amazing and everything like that. I will say about Colin that the first time I met him was like in a poster hall at AGU, and I saw him. He comes up to me, and I was like, "Whoa, this is like Bill and Ted's Excellent Adventure." What's going on here? But he took me over to his poster, and then it was like Bill and Ted's Excellent Science, and I was blown away, and I continue to be by everything that comes out of that group. So it's an honor to be invited to speak to you guys. Thank you. Okay, I'm going to tell a story today that starts with the sun and the Earth's orbit around the sun, goes through the great ice ages and through the ocean and into the mantle, and then comes back out and ends up on the ocean floor, where we see patterns of faulting that are really interesting and provocative. So I don't know, I mean, this is an engineering school, which is already a bit confusing, but let's say the Earth is not orbiting around the sun in a perfect circle. It undergoes variations of its orbital cycle. It undergoes cycles of variation of its orbit, including an eccentricity cycle, which is small variations on 100,000 and 400,000 year timescales, variations in tilt called obliquity on a timescale of about 40,000 years, and variations in precession, which are on a shorter timescale. And these frequencies, the frequencies of these oscillations, are connected to climate, and in particular the 40,000-year cycle controls the amount of insolation in the northern hemisphere summer, and therefore seems to be important in the accumulation or melting of ice on a planetary scale. So when we look at the record of ice on Earth, we see this sawtooth pattern, and I imagine many are familiar with this. So that today is at the right, and we're going back, looking at sea level as a proxy for the amount of ice that's on the continents. And the variations of sea level are up to about 120 meters. When the ice sheets have grown, sea level drops. And the Fourier spectrum of this signal has peaks at around the eccentricity timescale. You can see about a 100,000 year period, and also at about a 40,000 year period. And this has been known for a long time. It's what led people to ask the questions about how Milankovitch frequencies are affecting climate over these timescales. But down at the bottom of the ocean, things happen much more slowly. This is a representation of plate tectonics on Earth, and you can see that the white lines represent plate motion vectors, and at the red lines, plates are diverging and a new ocean floor is created magma is erupting onto the seafloor and forming the oceanic crust. And then the plates are steadily moving away from the ridges, producing more and more crust. And the crust is recording something about the conditions at the time that it formed, and so it gives us a record of past conditions with distance away from the ridge axis. So this is just to say that 80% of terrestrial volcanism takes place at the mid-ocean ridges, and half of the Earth's surface is kind of repaved every 100 million years. So it's a very active geological process and a very important one in understanding what's happening within the mantle, but also at the surface. And if we look at a cross-section in a kind of cartoon view, as the plates spread apart, the mantle upwells beneath. And that upwelling means that parcels of mantle are moving from higher pressures at depth to lower pressures as they ascend. And that decrease in pressure triggers melting. And the melt is buoyant, it's less dense, and it rises up to the ridge axis where it erupts. But if we look at the seafloor, what we see is a topography which is closely related to faulting. So this is a picture of the bathymetry next to the ridge axis, which is the deeper part in blue. And you can see these corrugations, and the seafloor is covered with these corrugations, except for where they're buried under sediment. So anywhere near the ridge axis where there's not yet a thick blanket of sediment has these abyssal hills correlation. So they're, in a sense, the dominant land feature of the solid Earth, but they're hidden beneath the sea. And they're bounded by faults. And we know that because of topography, because of submersible studies, because of earthquakes. And you can see the faults in detailed bathymetric maps. So the seafloor topography is fault-dominated. It's not dominated by lava flows. So a lot of detailed studies of the bathymetry have been done. There are ship observations from all over the mid-ocean ridge system. But there's particularly high-resolution bathymetry data at the places on this map that are marked with numbers. And where there's a data set of high-resolution bathymetry, you can go and take transects across that bathymetry and analyze the topography. And so, to know something about the timing of the formation of the topography, one needs to know the spreading rate, and that's determined locally by looking in the magnetics for the magnetic reversals. So we know when in the past the Earth's magnetic field has reversed, and so if we can find that reversal point recorded in the rocks, then we know the distance from the ridge axis and therefore the time from the ridge axis that reversal took place, and so we know the spreading rate. And these red dots are markers of the last magnetic reversal. So we know the time that happened, and we can therefore get the spreading rate for the ridge. And Peter Heuber's colleague in Harvard, who worked with this data, analyzed this with multi-taper Fourier spectra. So we know what is the frequency content at each of these transects, at each of these ridges. And so here's a picture of that. So on the y-axis are the different regions, from the fastest at the bottom to the slowest at the top, and on the x-axis is frequency, and the vertical dashed lines are the Milankovitch bands. So eccentricity, 100,000 years at the far left, and then obliquity in the middle, and precession at the right. And you can see that for the slowest spreading ridges toward the top of this plot, there's an obvious concentration of power at 100,000 years. And if we just knew that, we might say, well, that's curious, but maybe there's some, just geophysical fault spacing property that gives a 100,000-year spacing. But what's surprising then is that when you go to the faster spreading ridges, there seems to be this jump away from 100,000 years toward 40,000 years. And then the spectral density clusters around 40,000 years. And if we average these faster spreading regions, so we look at a spectrum which is the average of all their individual spectra, then you can see this very sharp spectral peak at 41,000 years, which is well above the the confidence limits for what might be emerge from random noise. So there's clearly a signal at 40,000 years associated with these fast-spreading midocean ridges. Okay, so these are the questions that I want to try to answer in the course of this talk. Why do Milankovitch frequencies appear in seafloor topography? Remember, Milankovitch frequencies are orbital frequencies, so there's subtle changes in the Earth's orbit around the sun. Why should they appear on the seafloor? And in particular, why is there a significant concentration of spectral power in the obliquity band at fast-spreading ridges? So what is transferring this frequency content from the orbit into the topography on the seafloor? And this is my hypothesis, our hypothesis. So the Milankovitch cycle enters a phase of lower solar energy in the northern hemisphere. And the climate cools, water is taken up into ice sheets, and sea level drops by 100, 120 meters. This leads to falling pressure on the mantle beneath the sea and an increased rate of melting because melting is decompressional. So then there's an increased crustal production during that phase and a delay of new faulting in the crust, leading to variations in fault spacing that might explain this frequency. So we're going to go through this in detail. This is just to show you that we can go from these cartoons of tectonics and melting to quantitative models that link the plate spreading with the production of melt. So what you see here is the result of a numerical simulation where mantle flows, like mantle convection, along these white solid streamlines and melts, and the fraction of melt that's present is given by the colors on a logarithmic scale. The melt is buoyant, and so it's rising up, and the white particles are tracer particles that move with the melt where it's present. So they rise up and get focused to the ridge axis. The dashed lines are isotherms, so those show the cold, rigid lithosphere that moves away from the ridge axis, and that's the tectonic plate. What's happening then, if we zoom into the very smallest scale, so where grains of solid mantle are melting, is shown in this slide. So this is an X-ray of an experiment from Wenlu Zhu's group, where the grains are shown on the left and the pores are shown on the right, and they've been segmented from the X-ray data. And the volume fraction of liquid to the total volume is called phi, the porosity, or phi. And what you can see is that even at low porosity, the pores are interconnected. So the melt can segregate out and rise to fuel volcanism at the surface. So we model this with partial differential equations. This is conservation of momentum and mass. And some will be very familiar with these sorts of things and others not at all, and that's totally fine. I'm not going to go into the details here. But the top two equations, the top one is the conservation of momentum for a liquid in the pores, and the second one is the stress balance for the aggregate, the two-phase aggregate. So solving these equations allows us to solve for the liquid velocity VL and the solid velocity VS. And then there's a porosity evolution equation where porosity changes due to melting and compaction, which is given by C, the compaction rate. And then we require that we can't sort of open up voids in the mantle or something like that. So that's the continuity equation. And to close these equations, we need to know things about rock mechanics, like the shear viscosity of rock, eta phi, and the compaction viscosity of rock, zeta phi. And we need to know the permeability. But we also need to know the melting rate, which is given by gamma. And that comes from petrological thermodynamics, which is a complicated subject. But it's crucial for what I'm going to talk about to have some simple model for the melting rate. And so this is a simple model for the melting rate. The rate of melting is given by this material property called the isentropic melt productivity, which is just how much melt do you make when you take a parcel of mantle from higher pressure and move it to a lower pressure. So that's something that you can do in the laboratory. You can measure that, or you can do it with thermodynamics. It's essentially a material constant. And then the second factor there is the rate of change of pressure, dP/dt. So the rate of melt production will scale with the rate of change of pressure. The faster you decompress the rock, the faster it melts. And changes in pressure come from two things. They come from mantle upwelling, so the mantle convectively flowing up toward the ridge axis as the plates spread, and from sea level change, right? So when it comes to mantle upwelling, solid density times gravity times the speed at which the mantle moves up, which is roughly the plate spreading speed, which we know. And then sea level change, which is the water density times gravity times the rate of change of sea level. These are just the static pressures involved in these two processes. So we can get a sense of the relative contribution of sea level to this by looking at the ratio of gamma S to gamma W, which is simply the density ratio, about a third, and the ratio of sea level change rate to upwelling rate, which also happens to be characteristically about a third. So this is something like 10%, which is, it's not, sea level is not the dominant control, but it's at a level which should be observable. So we expect that we might be able to see this, but we need to go a little further beyond the back of the envelope. So what we did was we took the numerical models, and instead of just having a fixed pressure at the surface, we forced the models with variations in pressure that are associated with sea level. And that's what's shown here. So the sea level reconstruction from delta 018 is the black curve at the top, and then the model output forced by that variation in sea level are shown in the colored curves below for a fast spreading rate and for different guesses about what the permeability is at a given porosity. So what the spectra on the right show is that, first of all, sea level has these Milankovitch frequencies once again, but that those Milankovitch frequencies are transferred into the melt production and delivery to the ridge axis. So we expect that the delivery of melt to the ridge axis will vary on these Milankovitch frequencies because sea level is going up and down. Okay. So you should never trust numerical models. We did some more simple analytical calculations where we treated this as a column and with a background melting rate and a background flux of melt toward the ridge axis, and treated sea level variations as a perturbation, which is formally small, and therefore we can linearize the equations and look for analytical solutions. And what the analytical solutions allow us to do is plot the frequency dependence of the response. And that's what's shown at the right. So frequency is on the x-axis. Again, the dashed lines are the Milankovitch bands. And the admittance, or the transfer function, the response of the midocean ridge system to variations in sea level, is plotted on the y-axis. And so you can see that at small frequencies, so very long periods of oscillation, sea level changes very slowly, the rate of change of pressure due to sea level is very small, the response is very small. But as you go toward higher frequencies, the rate of change of sea level is bigger, the melting response is bigger, and you get a peak at about the obliquity band. So that's where sensitivity to these sea level variations is high. As you go to high frequencies, the black curve slopes down steeply. The black curve represents an aggregate of columns going from the center of the midocean ridge off to the axis. And each of those columns are a little bit out of phase, and so the melt delivery is out of phase, and there's cancellation between the perturbations, and so you get a small response. So there's a clear peak at about the obliquity frequency. Okay. Is it observed? There's not a great deal of data out there on crustal thickness, and particularly crustal thickness far enough off axis that you can resolve these periodicities. But here is a place where people have measured the crustal thickness using seismic methods from ship active seismics. And you can see on the left the bathymetry and on the right the crustal thickness. And you can see that there's clearly crustal thickness variations, and they're at a level of about 10%. So qualitatively, the amplitude is about right. And Peter was involved in this paper as well, did the spectral analysis. So what you see is, again, frequency on the x-axis and now latitude on the y-axis. The left plot is for west of the ridge, and the right plot is for east of the ridge. And the pink represents large power spectral density. So you can see the power spectral density, again, in some cases aligning nicely with 100,000 and 40,000 year frequencies. In other cases, not so much, but it's a pretty small data set, and of course, anywhere you go, there's going to be a lot of noise. So it's not a very, very clear signal, but I think it doesn't refute the idea that there's spectral power in the Milankovitch frequencies and the crustal thickness as predicted by the models. So maybe this is supporting. All right. So is the topography of the seafloor then just this sort of isostatic response to these variations in crustal thickness? By isostasy, I mean that, you know, the crust has a density which is less than the mantle. It floats up a little bit where it's thicker. It floats down a little bit where it's thinner. And maybe the variations in thickness are what we see on the seafloor, not nothing to do with faulting. So some people who wanted to refute this said, well, you know, there's no isostatic compensation because the flexural stiffness of the plate is too big, right? And so these things can't float to their neutral buoyancy level because they would cause flexure in the plate, and the plate is too stiff; it won't flex. And so the variations that come from the Milankovitch frequencies are at a wavelength where flexure is dominant, and we can't have. So it must be due to faulting. So we need to somehow make a connection between these variations and faulting. So how are we doing with the hypothesis? Well, we've gone up to part 5, and I think shown that variations in sea level associated with climate can give you variations in crustal production. But what about faulting? You know, how do we make the connection with faulting? And this is where the meat of the talk lies. So it's faulting that causes the topography of these abyssal hills. So we need to model that. So one hypothesis that was proposed by Peter and colleagues was that tectonic stretching causes faulting, and in particular tectonic stretching where you have more or less magmatism. Because when there's magma at the midocean ridge, then dikes can be emplaced, and those dikes allow the plates to spread apart without faulting. When there's no magma at the ridge, the plates have to break by faulting to get extension. So this model worked very crudely. You could either turn magma fully on or fully off. So either the spreading was accommodated by magma or not. And then, you know, by imposing 100,000-year cycle on that on-off switch, you can look at whether faults form in this viscoelastic plastic numerical model, right? And sure enough, you know, you can get this to work. It will produce faults that are paced by this on-off switch of magmatism. And, you know, at high enough spreading rates, you can predict these frequencies of Milankovitch cycles because of this very crude model where magma is either 100% on or 100% off. But there's a problem with this, and that is that this predicts an axial valley at the ridge axis, and that's not what is seen at fast spreading ridges. So at the topography of midocean ridges has kind of two modes, and this is a principal component analysis of topography in the global midocean ridge system. So the first mode is an axial valley, and the second mode is an axial high, an axial ridge. And the first mode, you can see at the right, is mainly active at slow spreading rates. So, you know, mid-Atlantic and Indian Ridge, those have axial valleys. But at fast spreading rates, there's an axial peak. The midocean ridge is a ridge. And the model that I showed you before, aside from having this very crude model of magmatism, doesn't reproduce the ridge. So we need something that does. And looking back in the literature, there was a model proposed by Roger Buck. And what he said was that the ridge is high because of isostasy. It's hot, there's a lot of magma underneath, and the buoyancy of that hot and melt-rich rock pushes the ridge up. And it has this zone of diking where it essentially reaches its isostatic level. And then hydrothermal circulation cools the hot magma-rich rock, and creates an elastic plate. And it does so quite close to the ridge axis. And as it does so, the high topography is kind of frozen in by the cooling, and the plate has an ingrown curvature. So instead of wanting to be flat, it wants to be kind of curved upward toward the ridge axis. And when you uncurve it, then that induces stresses. So those what we call unbending stresses. It's born with this curvature, and then as it unbends, it gets stresses. And it's unbent by gravity-driven flexure in his model. So that's what I'm going to talk about. Now, let me first say that there's good evidence that this unbending process is what's driving faulting. Faults are active up to 30 kilometers away from the ridge axis, where the plate is thickened. And stretching faults, so by tectonic extension, would be clustered close to the ridge axis. And that's not what we see. All right. Magma supply is continuously present at fast-spreading ridges, so there's no shortage of dikes. You can always form a dike. And so that doesn't really help us with this faulting problem, because if there's always a dike, that's always the easiest way to accommodate extension. When we observe these faults, they dip toward the axis and away from the ridge axis. And tensile extension faults should always dip toward the axis where the plate is thinner. And then there's this last point about frequency distribution of fault length, which is interesting, but I'm not going to go into it because it would take too much time. So there's this evidence that bending faults might be more plausible explanation for what we observe than stretching faults. So here we are in the Department of Engineering. Let's talk about beam bending, because everyone loves beam bending. It's a fantastic, wonderful theory with a lot of explanatory power. Okay, so the Euler-Bernoulli theory of beam bending. So first we have to talk about the kinematics. We're going to define this thing W, which is the vertical displacement of the plate. So so Y will be equal to W as a function of X, and then the plate will have a thickness H, and there's some length scale L over which bending occurs. And you can think about this in terms of a radius of curvature and the longitudinal strain. So if I had a fiber that was going down the plate, the strain that fiber would experience is related to this radius of curvature and the position within the plate. So here, if you go to a fiber at the top of the plate, it's been compressed, and a fiber at the bottom of the plate has been extended, and the amount to which they've been strained is related to 1 over r. Now, if the thickness of the plate is small compared to the radius of curvature, then we can approximate the radius of curvature by the second derivative of W. You can see where this is going. We want to derive a partial differential equation. So 1 on r is about the second derivative. And so the strain is therefore proportional to yw prime prime, second derivative. Okay, for those of you who are mechanical engineers, this is getting really boring. But for the rest of you, let me go on. So we want to now relate stresses and strains, and we're going to do that using an elastic model. E will be the modified Young's modulus, which takes into account Poisson's ratio. And the moment, the bending moment, is the integral of the fiber stress across the height of the beam. And that has this factor of y in it. And so when you substitute then for the strain, according to the constitutive law that relates stress and strain, then you get a y squared, and when you integrate that, you get a y cubed, which evaluates as h cubed. So then you've got this h cubed, this thickness cubed in the beam bending, and that's the second moment of area, and it's going to be very important in what I'm going to talk about, because what we're going to talk about is variations in h. And those variations are going to be important because the whole problem is related to h cubed. Okay? So I of x is the second moment of area, and that'll play a role in what's to come. Now, I want to go back to what I said before. This plate is not born flat, right? So it has a neutral curvature. And that neutral curvature is called kappa. And so it's only the difference between the curvature that it has and kappa that gives us stress. When w prime prime is equal to kappa, so when it's in its neutral state of curvature, then it's happy, it has no stress. Okay? So we have to look at this difference, w prime prime minus kappa. There it is. Okay, and now we need to relate this to a force balance, which just says that The second derivative of the moment is going to be equal to the load Q that's on the plate. And so we end up with this differential equation where you see W prime prime minus kappa. And then the second derivative of all that is equal to the load Q, and I is related to H cubed. All right, so what is the load? Well, this comes from the isostatic forces. So the plate wants to sit at the level of that dotted line, then it would be in balance isostatically. But if it's undulating away from that, then the pressure in the mantle is higher where as you go down. So this wants to push the plate back to its neutral level. So places where the plate has been depressed want to rise, and places where it's been lifted want to sink, and this is the load Q on the plate. And it's proportional to the displacement itself. So we end up with this differential equation where we've replaced Q with delta rho GW. Delta rho being the difference in density between the water and the mantle. Okay. So here's the hypothesis now that we've got this theory. So the axial high is due to the buoyancy at the ridge axis, and the plate is born with this positive ingrown curvature. And then as it moves away from the ridge axis, it unbends, it flattens out due to gravity. It wants to go onto that dotted line. It wants to lie flat compared to gravity. So it's unbending. And as it unbends, you get tensile stresses at the top of the plate and compressive stresses at the bottom. And those tensile stresses are what is causing the faulting. So we need a little bit more modeling. At the ridge axis, the buoyancy is related to the plate thickness and also to this density ratio, which I'm going to call R, which is related to the density difference between water and the mantle and between the ridge axis, rho A, and the mantle. So R is a control, and the thickness of the plate is a control. But the most important control is kappa. And kappa is estimated by saying that it's the second derivative, so we take the height, the relief of the ridge axis above the far field, and divide that by 2 times this bending length L. So that bending length is giving us the length scale over which bending takes place. Right? So you've got 2W naught over L squared, and L squared is an intrinsic length scale for this bending problem. It's called the gravitational bending length scale. In the bottom are the forces that restore the plate to being flat, and in the top are the forces that resist that. So the length scale is given by the length over which those things can balance, and it's about 15 kilometers for the plate. And then these stresses are going to emerge. All right, so we can look at the differential equation in non-dimensional terms, and there it is, and it's got a nice analytical solution, which is plotted there. The high at the ridge axis, and then there's a little overshoot, and then it comes back up to 0 in the far field. And this matches beautifully with the topography of midocean ridges, with no special tuning of the model. So just, if you have the right bending length scale according to the plate thickness, then you can match the topography of midocean ridges nicely, and that gives us some confidence that we've got. Let me check the time here. How am I doing on time? Okay, good. That gives us some confidence that we've got the right model for the topography of the ridge. There it is compared to the principal component. Okay, but the variations in sea level are, hypothetically at least, giving us variations in the thickness of the plate. So those plate thickness variations are pretty small. We're not talking about a factor of 2 or 10 or something like that. We're talking about 10%. Or maybe less. So let's treat those variations as a small perturbation and do a perturbation analysis of this theory. Right? So we'll take H to be H naught, the plate thickness, something like 7 to 10 kilometers, and H tilde will be this small perturbation due to sea level variations, and it will be periodic, and we'll use a sinusoidal dependence since we're going to linearize everything. So the wavelength is the plate spreading rate divided by the frequency, and the frequency is, say, 40,000 years. That's, the period, so the frequency is 1 over 40,000 years. So we can build this variable plate thickness according to our hypothesis about sea level control of magmatism. Okay, so we can then do some mathematics won't go into the details, but the idea here, if you've ever seen perturbation analysis, is that at leading order, you have the background state, which is exactly what Roger Buck proposed and what I showed you the solution to. And that's this variables with the zero, so W naught, fourth derivative is equal to minus 4 W naught. That's the classical beam bending problem. And what's below is the new part. So this is the equation governing the perturbation. So it's saying, what is the consequence of these variations in thickness for bending stresses or for bending displacements? So we need to solve the second equation. We also have perturbations to the boundary conditions. So these are the boundary conditions that Roger Buck used, everything uniform. And these are going to be the conditions that we'll use. You see that they're dependent on the plate thickness, which is time and space dependent. Okay, so of course there's a solution. We've already seen the solution for the base state, and it's fairly simple. It's in the top line. What's remarkable is that you can actually solve analytically for the perturbations, and that's what's shown in the next line. It's a little bit messy, but it's not too horrendous as long as you put these constants A, B, C, and D into that concise form. If you write them out fully, then it's a horrible mess, okay? Thankfully, we have, computer algebra, because I would never, ever have been able to do this without making horrendous mistakes. But this is right. I checked it against numerical solutions and everything. And if you take the limit of large... Sorry. Neil Young. Okay, we're okay though. We okay? All right, everyone's ears okay? It's good that you're now all awake, because it's just going to get more exciting here. So if you take the limit of large K, then these things actually simplify quite a lot. And I'm going to be doing that is just looking at the large K limit. Anyway, so from this solution for W, we can reconstruct the bending moment. So we're getting toward the stresses, and this is the base state. So this is what Roger Buck found, and now we can look at these perturbations, which are time dependent. So they're oscillating up and down, but they have this structure, right? And they have if you look at the K going to infinity, that's the large wave number, so small wavelength limit. They have this maximum, which is, about 10 kilometers from the ridge axis, so right in the right place to perturb the faulting. Okay, now we can reconstruct the stress from the moment, and so we get this expression here for the stress. It has the base state parts and it has the perturbation parts. And if we look at the size of the perturbation relative to the base state, then we get this simple expression. This is for large K, where it doesn't decay as you go to large K. So for very small wavelengths, you can still have big perturbations in the stress, right? And those perturbations are going to go as 3H. H is the relative size of the variations in plate thickness. So if you have 10% variations in plate thickness, then you would expect 30% variations in stress. And 30% is big, and the reason it's big is because of H cubed. It's because the second moment of area goes as H cubed, and that's why there's this 3H. When you linearize H cubed, you get 3H. Okay. So here's the solution. The top panel, it's a movie, help you stay awake. The top panel is the Buck solution. Red represents tension, and blue represents compression, okay? So you can see the surface of the plate is in tension, but it's pretty boring because there are no perturbations. And it's just saying that there's this uniform, as the plate unbends, you develop this uniform tension across the surface of the plate, right? Maybe you get uniform fault spacing from that. But if you introduce a perturbation, then the perturbation leads to variations in the stress, as we've just computed, right? And there are different contributions to that. There's the M naught over I1 contribution, and then there's the M1 over I naught contribution. Now, it turns out that the M naught over I1 is really big, which means that we didn't have to bother to go to all this trouble to solve for M1, which was such a pain. We could have just guessed by saying we know what the solution is at the top, and we know what the variation in thickness is, and so we just use those two. But of course, we didn't know that, so we did the whole problem. Anyway, when you add all these things together, what you can see is big variations in stress, and that should localize faulting to places where you have thinner lithosphere. Okay, now the thing about this calculation is I've really exaggerated, to make it look pretty, I've exaggerated the parameters, right? So we have a long wavelength, and we have a very big plate thickness perturbation. And that's a bit unrealistic. So here are some realistic parameters. I'm not going to go through all of these, but let me point to the dimensionless ones. K shouldn't be 5, it should be something like 30. R is about right, and H should be about 5%. So we have a peak to trough variation of 10% in plate thickness. Okay, so if we then do a calculation with those properties, then what we get here is that although the wavelength is smaller, the relative size of the perturbation is still about the same. Okay, and that's because of this asymptotic limit that I showed you. It scales as 3h. Doesn't matter what the wave number is. Once you go to large k, there's no dependence on k anymore. So you get these big perturbations in the stress, even if you have small wavelengths, as we have here. Okay, so we've got variations in stress, but this is all about faulting. And how do we say something about faulting? So we can apply the same mathematical idea of linearization to the fault spacing and say that there's a reference spacing x0, and then there's some perturbation to that reference spacing x1, and we're going to linearize. And by now, I think you've probably had enough of hearing me talking about linearized things. So let's just say that by applying this method, we can solve for x1 if we say what x0 is. So if we go out and measure the mean spacing of faults, then we can predict from this analysis what the perturbation to that mean spacing should be. And there it is analytically, as you don't care about that. But now let's look at the plots of this. So look at the k equals infinity, going to infinity, the red curve. And on the x-axis, we've got x0 over the bending length. And if the typical spacing is 2 kilometers and the bending length is 15 kilometers, then that gives us our position on the x-axis. If h tilde is 0.1, so I said it was going to be 0.05, but now I've said it's 0.1. Sorry about that. It's all, sort of the same order of magnitude. Then we can see where we are on the y-axis, and it turns out that that is at about 40%. So the spacing of faults can vary by plus or minus 40%, and that's really big, okay? So we can confidently say that if we have these variations in the elastic plate thickness, and unbending is the mechanism for faulting, then the fault spacing will definitely vary with the variations in plate thickness. Okay, but what we need to do next is actually model the faulting, because it's really not satisfying to say we're going to apply a perturbation theory to something discrete like fault spacing. So we need a model that actually handles the formation and the evolution of faults, and more importantly, how they interact with the stress field and therefore with neighboring faults. Because you'd be surprised to find two faults very, very close to each other. Once one fault exists, it relieves the stress, and another one's not going to form right next to it. So there has to be this interaction, in addition to the stresses that come from unbending. So we need to model faulting and therefore predict the topography, and then take a spectral analysis of that model and compare that with the data. I hope I've convinced you, though, that it's very plausible, given the stresses, to think that the faulting would follow this pattern of 40,000-year oscillations. So here's a summary, because I guess there's been a lot of detail, a lot of Euler-Bernoulli bending theory and so forth. So I want to step back and just emphasize the kind of remarkable nature of this observation and the chain of ideas that go into modeling it. So we know that the Earth's obliquity is varying through time. Its tilt in its orbit is varying, and this has contributed to climate change at 40 and 100,000 year cycles. And that's moved massive amounts of water out of the oceans and onto the continents, which has really changed the state of pressure in the mantle beneath midocean ridges. And we know that mantle melting is pressure dependent, and so moving that water onto the continents has varied the melting rate, and that has varied the crustal thickness, right? And then we looked at this bending problem and showed that that leads to variations in stress, and it's stress that causes faults. So that variation in stress could lead to a variation in fault spacing and therefore to orbital cycles being inscribed on the ocean floor, where you might least expect to find them. So with that, I'll put up some summary and leave you, if you want to read it, please feel free. And just say thanks for your attention and for inviting me.